Wasat Center is one of the centers established in May 1955. The center acquired 139 hectares farm along the right bank of River Mahi, which is representative of the problem of the area, in 1956. Subsequently, the administrative control of the center was transferred to the Indian Council of Agricultural Research on 1st October 1967. R&D activities of the center focused on evolving strategies of soil and water conservation on watershed basis, tackling special problems of ravine reclamation. A complete package of practices has been developed for protection of ravines while putting it to productive utilization. Popularization of watershed management concept and technologies, strategies for groundwater recharge and management, demonstration of technology and imparting training are important activities of the center.
इस काम से हम किसानों को लाभान्वित करने की पूरी कोशिश कर रहे हैं कि उनको कृषि के लिए पानी मिले। कृषि में पानी के लिए जो बरसात का पानी है उसको इकट्ठा करने के लिए हम बहुत सारी तकनीकें गांव में बता रहे हैं, लेकिन इसका जो एक उदाहरण जो लाइव उदाहरण हो, सजीव एक वो उनको दिखे किसानों को, इसके लिए हम एक डेमो भी हर जगह डेमो यूनिट बनाते हैं। और मैं आभार प्रकट करती हूँ संस्थान का, मृदा एवं जल संरक्षण संस्थान का, कि उन्होंने कृषि विज्ञान केंद्र के परिसर में भी एक रिचार्ज पिट बनवा दिया था, जिससे बरसात का जल को हम बोर में रिचार्ज कर सकते हैं। क्योंकि ये जो क्षेत्र है, चमहल है, दाहोद है, छोटा उदयपुर है, ये अर्ध शुष्क क्षेत्र है। यहाँ पे बरसात अपेक्षाकृत थोड़ी कम होती है और वर्षा का पानी को एकत्रित करने के संसाधन भी थोड़े कम ही दिखते हैं। ऐसे में जो बोर किया जाता है या कुआं है, उसमें बहुत थोड़ी देर के पानी तो रहता है, पर वो बरसात के कुछ दिनों के बाद उसमें पानी बंद हो जाता है। बोर में 10 से 15 मिनट पानी चलता है। साथ ही जो पानी का खारापन है वो भी काफ़ी अधिक होता है। तो ऐसी स्थिति में जो ये रिचार्ज पिट बनवाया गया है, ये जो तकनीक इन्होंने विकसित की है और इसका डेमोन्स्ट्रेशन कृषि विज्ञान केंद्र में भी रखा है और गाँव में भी किसानों के खेतों पे भी जो बोर हैं या कुआं है उस पर लगाया गया है, इसके बहुत ही अच्छे परिणाम आए हैं।
The easy accessibility of groundwater by even small-scale users, its local availability, and difficulty of coordinating and governing many users of the same aquifer across wide geographic spaces has frequently led to indiscriminate extraction of this precious natural resource for domestic, industrial, and agricultural uses around the world. Groundwater exploitation, particularly in India, has increased by leaps and bounds. Over the last 50 years, along with the expansion of shallow, mostly private wells, at the same time, changes in the hydrologic regimes, in particular, the growing scarcity of surface water supplies as agricultural and other users have expanded, have pushed water users to seek groundwater alternatives. The natural recharge studies carried out over different hard rock terrain indicated that only 5 to 10% of the seasonal rainfall recharges the groundwater. The meager annual replenishment of the natural recharge to groundwater alone with multiple uses may not be able to meet the projected water demand of 17,000 million cubic meters per year by 2050. To respond to the growing groundwater crisis and take advantage of the high levels of runoff not captured by natural recharge, augmenting groundwater resources through artificial recharge of aquifers has become widespread in India over the last decade. ICAR, Indian Institute of Soil and Water Conservation Research Center, Wasat, located in Anand district of Gujarat, has developed a sand-based runoff filter to capture the runoff from farmers' fields to artificial groundwater recharge. The runoff harvesting and its recycling through groundwater recharge is the flagship technology of the circular economy.
જે કેન્દ્ર સરકાર દ્વારા સ્થાપિત જળ અને જમીન સંરક્ષણ સંસ્થાન જે ખેડૂતોને અવિરત આ દિશામાં ક્ષેત્રે જે ટેકનોલોજી વૈજ્ઞાનિક સંશોધનો થયા છે તેને અપનાવવા માટેના પોતાના પ્રયાસના ભાગરૂપે આ વિસ્તારમાં સર્વેમાં નિકળ્યા હશે અને સર્વેમાં નિકળ્યા પછી આ વિસ્તારમાં એટલે અમારા ગામમાં આવી પહોંચી અને ખેડૂતોનો સંપર્ક કરી અને ખેડૂતો પાસેથી આ વિસ્તારમાં જે સમસ્યાઓ ખેતીને લગતી હતી તે એમણે પૂછી અને એમણે પણ જાણી અને પછી ખેડૂતો સાથે એનું શું સમાધાન થઈ શકે છે તેના પણ જે સ્ત્રોતો હતા તેના પર વિચારણા કરી વિચાર વિમર્શ એકબીજાના અભિપ્રાય જાણી અને સમજીને પછી ધીરે ધીરે અહીંયા જે કોતરો જઈ રહ્યા હતા તેના પર ચેકડેમ કેટલા અંતરે ગુજરાત સરકારે બી એમના તરફથી કંઈક થયા હોય તે સિવાય બીજા છૂટી ગયેલા વિસ્તારમાં નવા ચેકડેમ કેટલા બની શકે છે તેનો પણ સર્વે કરી અને તેવા પ્લાસ્ટિક જે ઓછા નાણાંના રોકાણથી બી બની શકે તેવા પ્રયાસના ભાગરૂપે પ્લાસ્ટિકનો ચેકડેમ બનાવીને એક અભિગમ બતાવીને ખેડૂતોને આસપાસમાં જે કંઈ બોર કૂવા થયેલા હોય ડગવેલ હતા તેના પાણીના સ્તરને ઊંચું લાવવાના એક પ્રયાસ રૂપે એક સફળ પ્રયોગ થઈ શકે છે.
The runoff estimation for the design of runoff filters was carried out using the USDA SCS curve number method, and the Webull method was used to find out the design runoff at 80% probability using Webull's distribution for the semi-arid regions of central Gujarat. The peak runoff rate was computed using rational formula. The time of concentration for overland flow was computed using the Kirby method for overland flow. The selection of suitable material for the construction of runoff filters should be based on a gradation curve using mechanical analysis of different sizes of available filter materials. The materials should be arranged in ascending order of their sizes, namely fine size material on the top and coarse size material at the bottom of the runoff filter. The two criteria of permeability and stability of filter layer is required to be contended. The design criteria were developed by the US Bureau of Reclamation, Winger and Ryan 1970, and the USDA Soil Conservation Service SCS 1988. In the case of the uniformly graded filter and base material, that is, material is lacking the excess presence of certain particle sizes, a filter stability criteria ratio of less than 5 is generally considered as safe. The recharge rate through the filter is governed by Darcy's law. The hydraulic properties of the top layer of the runoff filter having finer material, that is, sand, govern the recharge rate. The particle size and its distribution, permeability of the sand layer, the surface area of the sand layer, thickness of the sand layer, and the head runoff over the top surface govern the recharge rate and sediment trap efficiency through runoff filters. The other coarser layers beneath the finer material layer just provide the support required to hold the finer layer. The main filtering of runoff is carried out by the top finer layer. The filter runoff can suitably be conveyed through PVC pipes of appropriate carrying capacity to recharge the dug wells, tube wells. The optimal design of runoff filters with 3 layers of coarse sand with particle size distributed between 0.2 to 2 millimeters, gravel with particle size distributed between 6.5 to 19.7 millimeters, and pebbles with particle size distributed between 19.7 to 30 millimeters should have a thickness of each layer in the ratio of 1:5:1:3. The additional layers of charcoal and potassium permanganate or other suitable chemical treatment is required to remove the microbiological contamination to make it suitable for drinking purpose. The hydraulic head recharge rate was measured using the stage level recorder and 90-degree V-notch. The runoff charts from the stage level recorder were digitized using Surfer software to compute the hydraulic head and recharge rate. The runoff samples entering and leaving the runoff filters were manually collected on the downstream side of V-notch for assessing the sediment trap efficiency of the runoff filters. The runoff samples were dried in the oven and weighed in the physical balance. The sediment per unit of runoff was multiplied with total runoff generated during a particular rainfall event to calculate the sediment at the inlet and outlet of the runoff filter to get sediment trap efficiency. The runoff filters were designed for 0.4 hectares farm size, usually available with most of the farmers in the semi-arid regions of Gujarat. The design runoff for the filter design was estimated using USDA SCS CN method at 80% probability as 125 millimeters. The optimum size of the runoff filter was found to be 6 meters square. The material used in the construction of runoff filters layers is based on a particle size gradation curve obtained using wet sieve mechanical analysis in Yoder's apparatus. The filter materials were arranged in ascending order of their sizes, namely fine size material on the top and coarse size material at the bottom. The permeability criterion for runoff filter was found to be 16.42, which was within the range, that is 12 to 40. The stability criterion of the runoff filter was found to be 1.09, which was less than 5. The equivalent hydraulic permeability of the runoff filter was found to be 2.56 times 10⁻³ meters per second. The hydraulic head of water in the recharge filter was fixed at 30 cm. Considering the height of the bund usually constructed by the farmers in their field. Initially, the peak recharge rate of both the designs of runoff filters was similar in the range of 4.45 to 4.65 liters per second, which was obvious due to similar filter materials used, the analogous thickness of different filter layers, and identical cross section. The average annual decrease in the peak recharge rate of downward flow runoff filter was 51%. The average annual increase in the sediment trap efficiency of downward flow runoff filter was 18% per year. The sediments get entrapped in the top 10 cm of the sand layer of the downward flow runoff filter, which reduces the hydraulic permeability of the sand layer exponentially. The removal of the top 5 cm of sand layer of the downward flow runoff filter design could recuperate 70 to 80% of the hydraulic permeability of the sand layer. The sediment trap before the runoff filter was able to trap 42 to 45% of the sediment in the runoff per year, which is required to be removed at least twice a year. The sediment deposited on the top surface of the sand layer of the downward flow runoff filter is required to be removed more frequently, at least 5 to 6 times per year, depending on the sediment concentration in runoff coming from the crop field for the adequate performance of downward flow runoff filter. The average annual decrease in the peak recharge rate of downward flow runoff filter was 15%. The average annual increase in the sediment trap efficiency of downward flow runoff filter was 6% per year. The hydraulic permeability of the sand layer of the upward flow runoff filter was relatively less, reduced from 7.0 times 10 raised to minus 4 meters per second to 6.5 times 10 raised to minus 4 meters per second per year. The sediment trap before the upward flow runoff filter was to reduce 82 to 85% of the sediments in the runoff per year. The sediment deposited in the sediment trap is required to be removed 4 to 5 times per year. The economic analysis was performed for comparing the benefits of constructing the runoff filter to enhance the performance of open wells, bore wells, with the cost of construction and the cost of annual maintenance. The average annual recharge through runoff filters varied from 2,380 meters cube to 16,580 meters cube. The groundwater recharge through the runoff filter was primarily extracted for irrigation, which varied from 648 meters cube to 9,216 meters cube at different locations in Gujarat. The water application was reflected in crop yields realized on these farms located in Gujarat. The additional area brought under irrigation due to enhanced groundwater recharge and the cropping systems practiced in each open bore well command were analyzed for returns from water use. The average return to groundwater uses for the runoff filters was estimated as Rs 5.35 per meter cube, and the average return to cost ratio for runoff filter worked out to be 2.24, which shows that the investment in the runoff filter is financially viable.
सपनों की छाँव में मेरे गांव के बढ़ते जाएं कदम, लहराए फसल हुंकार भरे जब खेत में टफ हरदम। सपनों की छाँव में मेरे गांव के बढ़ते जाएं कदम, लहराए फसल हुंकार